Andrea Bertazzi from École Polytechnique, and he will be talking about piecewise deterministic generative models.
Thank you, Yorgos. So, as you have seen for the past 2 minutes, okay, I will talk about piecewise deterministic generative models. Okay, the work that I've done with some people in Paris, in particular Alain Dormus and Dario Shariatian, who were my main co-authors, and also Moussim Zekli and Eric Mouli. Okay, so since anyway we're not really at a generative modeling workshop, I will start with an introduction, okay, to diffusion-based generative models to give you a bit of an idea of what people have been doing for the past couple of years. And I don't want to assume anything, so actually what is the difference between generative modeling and sampling? Okay. So in sampling, what we have typically is an analytic expression for a probability distribution pi, right? And what we want is we want to obtain samples from pi. Okay, this is a classic MCMC framework. But in generative modeling, actually, we have the same goal. So we want to obtain samples from pi, but we don't have an expression for pi. We just have realizations from it. Okay. So we will have a data set, x1 to xn, right, from a distribution that we don't know anything else about, apart from this sample. And what we want to do is obtain more samples from pi. And I guess you're all aware that generative models work successfully because we all use ChatGPT or these types of technologies these days. And there have been actually several ways to do generative modeling in the past 10 years, okay, starting from GANs, variational autoencoders, normalizing flows, and in the last 3-4 years, diffusion models, which are now really the benchmark for certain tasks, at least. Okay, and in this talk, indeed, I will focus on diffusion models. So here I want to, in one slide, give you the basic idea of how a diffusion model works. Okay, here I'm making many choices, and hopefully the easiest choices, okay, that I could make. And so what we have is we start with an Ornstein-Uhlenbeck process, okay? And essentially what we do is say we have a pi distribution that is a bimodal. Okay, in this case, I'll call this mu star. Okay. So what we're doing is we are initializing our OU process from mu star. Okay, so let's say if I draw a sample here from mu star, and then we will fix a time horizon, TF, and what we will do is we will just simulate, okay, a diffusion until time TF. Okay. So this is all we're doing. And what we have obtained now by construction will be that at time TF, if TF is large enough, the distribution of this process is approximately Gaussian, right? Okay. And so this is our starting point. And essentially what we're doing is we're starting from an initial condition that is difficult, and we're going to a limiting distribution which is easy. So this is exactly what we want to do in MCMC, at least the limiting distribution. So it's a weird MCMC, okay, scenario in which we start from something weird and we convert to something easy. But now we want to do generative modeling, right? So what actually makes sense is to revert time, right? So what we can do is we can initialize a process from a simple distribution, from a Gaussian. We can go back in time, okay? So instead of going forward, we start from an easy thing and we go backward. And at time TF, we will be at mu star, right? So technically, what's the time reversal? Well, if we call PT the density of the forward process at time t, the time reversal is just the process that at time t has the law of the forward process at time TF minus t. Okay. So of course we will start here. So if this, right, is the time that we consider for the reversal, the law is the same of the forward at TF minus t. And it turns out, actually, this is classical theory in a paper by Anderson in 1982, okay, and then by other people. The reverse process also satisfies an SD. In the SD, we can characterize it, we can write it down. Okay, and notably, we will just start at the backward process at PTF, so at the final condition of the forward. And importantly, doing this scheme and simulating the backward SD for time TF, we will indeed get back to mu star. This is by construction. Okay. Now, think of, instead of a mu star that is just a simple bimodal, think of having a distribution on images of dogs, on pictures of dogs, right? And this is our initial distribution. Then abstracting a bit, we can imagine doing following a forward SD that turns this data point to noise. Okay, so we will reach a time horizon, in this case t, so I took this diagram from a paper by Song and co-authors. Then we always have an expression for the backward SD, which is shown in the slide, the reverse SD, which brings us from noise to that data point. So of course we will not get back to the, well, we will get back to the exact data point if we really have access to this SD, but in practice this will not be the case. Okay. Now, as you might have seen, of course we cannot really simulate from that SD. Right? Why? Because we need access to that, what is called a score. So it's a gradient of log PT. So PT, of course, depends on mu star, right? Because it's the law of the forward process at time t, but it is initialized from mu star. So it is exponentially forgetting about mu star, but nevertheless, mu star is there for a small t or so. And so the first approach that we can follow is to say, well, okay, we are in machine learning here. Okay, so what we do is we just need a loss function. Once we have a loss function, we just throw a neural network at the problem, and we learn a neural network. Now, of course, there will be good and bad loss functions. But the first idea that one can have is, well, we just take an L2 loss. We take an expectation with respect to PT. Okay, and here I'm integrating with respect to time because I want to learn the score for all times between 0 and TF. Nice, so this actually, if we can minimize this or an empirical risk minimization version of this, then we're done, right? But the problem is, of course, this loss depends on the score, and we don't have access. This is an unknown quantity. So by doing just a few manipulations, actually, it turns out that we can rephrase the loss above as written below, and we go from this explicit score matching, so-called explicit score matching framework to the denoising score matching framework. Why denoising? Well, because here you see we don't have the real score anymore, but we have the score of PT given 0. So what is this? This is the law of the process at time t given the loss. So sorry, it's the score of the density of xt given x0. Okay, so this is known because we're choosing a super easy process, we're choosing an Ornstein-Uhlenbeck process. So this is really just adding Gaussian noise to our initial condition. Okay. And as it turns out, right, these two losses are equivalent, so we can just use the one below. And this is a valid loss function that we can minimize empirically. So what we will do again is we will draw, just to be clear, and give some more details. We can draw a time t randomly, let's say uniformly between 0 and TF. Then we will draw a data point from mu star. Okay, we have a data set, so we can do that. We just take one data point. And then we simulate forward in time for time t. Okay. And we minimize this. So here there are three types of approximations that we need to do. So the first one we have already seen, right? So we started from the real reverse time SD. There was something we didn't know, the score, and so we have estimated it, right? So now what happens is we have our neural network here in the drift. But this is not enough, right? Because here we still needed to start our backward process from PTF. But PTF, again, depends on mu star. We don't know that. Okay. But if TF is chosen large enough, and in practice is not that large, okay, don't think of 1,000, but actually 10. What we can do is we can replace it with a Gaussian, with a limiting distribution. So we make a second approximation. And now this SD has one less problem, at least. The third thing we need to do, of course, is we need to simulate the reverse time SD, right? And this you can do with any integrator, any solver that you want, an Euler scheme, or anything else. And in the end, what we have obtained is a procedure, right, that gives us a way to sample from the data distribution mu star. Okay. Now, again, abstracting a bit, what do we need actually to do generative modeling? So we need some data. First of all, without data, we cannot do anything. It's all we have. We need to choose a noising process, so a way to turn data into noise. For this forward process, we will need to be able to write down a time reversal, right? Because the interesting direction is the one backward in time. And then we will need a method to approximate the backward process. And so in this talk, what I want to discuss is using some other processes other than diffusions to do this task. Okay. And so this brings us to PDMPs. So Kengo has already talked about PDMPs, and also yesterday we heard about them from Paul. But still, I will give a very brief introduction. Okay. So PDMPs in the mathematics literature have been around for 40 years at least, and they have been successfully used to model various phenomena, okay, from crack propagation to risk theory and mathematical biology. Okay, and in the last few years, as we all know very well, we have used them for MCMC. So if I consider a homogeneous PDMP, a time homogeneous, as Kengo was saying, this is identified by a triple. Phi lambda q. And in particular, phi will be our flow map. So okay, again, we think of a particle moving in space according to phi. And then randomness comes in at random times. The random times have distribution that depends on the rate lambda. Okay, so it's just essentially just a non-homogeneous Poisson clock. When this rings, we will jump according to q. So q may or may not be random. Anyway, motivations for sampling, I don't even need to mention them. But motivations for generative modeling, first of all, PDMPs are really different from diffusions also in the context of generative modeling, in the sense that several diffusion models share really some similarities. Okay. But for instance, you can even do flow matching, so you use just an ODE to generate data where the randomness is only in the initial and final condition. And these are, in a way, you're just doing diffusion models. But for PDMPs, you cannot really make it fit into the diffusion model literature. Then it's easy for PDMPs to deal with restricted domains. So if you think of images, right? Well, images live on a bounded space. And if you want to do a diffusion there, you will need to reflect off boundaries, which is a bit more difficult than for PDMPs. And for similar reasons, you can also imagine dealing with Riemannian manifolds in a slightly easier way compared to diffusions, at least. So this is just to name a few reasons why we thought it would be interesting. Okay, so let's use PDMPs as a forward process, but first, perhaps, for the people that haven't seen PDMPs in the wild before, so this is how a PDMP looks like. Okay, you see we have these deterministic dynamics, and at random times there's a sudden change in velocity. Okay. So these are my three favorite PDMPs. Let's say.
It doesn't have to be straight.
It does not have to be straight, and indeed it's not in the center one. So the center one is actually following Hamiltonian dynamics. Okay. So if you remember what I talked about before, the first thing that we needed to do generative modeling was a time reversal formula. Okay, so this was the first thing we had to do. Again, so let's think of a PDMP with the three characteristics that I discussed before, so phi, lambda, and q. And let's say we start with initial condition mu0, and okay, we have a semigroup PT. So what we could show, what we can say under some actually technical conditions, but nothing too bad, just about stuff with the generators, of course, domains of generators. Okay, is that the backward PDMP, so the time reversal of the PDMP that I introduced above, has the characteristics in the slide. So we have a flow map that essentially is what you expect it to be. So you're just changing the direction of time. So you're going in minus t instead of t. Right? So here there's a minus t. And then the jump rates and kernels, okay, are the two green ones, and they satisfy a balance condition. Okay. So what does the balance condition say? So essentially, if we look at the right-hand side, here we are drawing a point z from the law of the process of the forward PDMP at time tf minus t. And then here we have the rate of jumping when we are at z, and then the probability of going from z to dy. Okay, so essentially we draw a point dz at time tf minus t, and we want to see what's the chance that we jump to y from there. On the left-hand side, we are sampling the point dy from the law of the process, and then we want essentially that the instantaneous rate and jump density of jumping from this point y to z, okay, equals this for the forward, right? So essentially it makes sense because we're going back in time. So we want to have the same probability that we had in forward in time. We want it to go back. Not particularly clear, but I hope at least you have an idea. And okay, I must say, we obtained this result, but Conforti and Leonard had a nice paper about this topic, not really necessarily citing PDMPs, but they did most of the work. Okay, our work was understanding their paper, which was not easy, to be honest, and applying it to our context and checking all the conditions that they require, adapting them to the PDMP case. Yeah.
The backward rate and the Q, they depend on T as well, or is this?
Right, that's a good point. So that they depend on T. Even if the forward do not depend on T, the backward have to depend on T. They wouldn't if you were in stationarity, right? That makes sense. But if you're not, then right, there is dependence on time. Yeah. Okay, and so here I adapted the diagram we saw before. So I hope Song and co-authors do not they are not unhappy about this. But again, we can start from our picture of a dog. Okay, and in this case, we're doing a forward PDMP to noise the data, whereas before we were doing a diffusion. And now we know how to go backward. Okay, we just need to find lambda and q that satisfy the balance condition. Okay, and here I use a different notation, but it's just do the reverse time flow. Right. So now we can go on to zigzag sampler, which we have seen before, so that's very nice. Zigzag sampler is a PDMP, right, with a position xt that lives on Rd and a velocity that is constrained on plus minus 1 to the d, right? The stationary distribution in general will be pi of x, where you choose your own pi of x, and the stationary distribution for the velocity is just a uniform on the state space for d. Again, what we have for a zigzag is just linear deterministic dynamics. What is slightly more complicated, if you want, is what happens at jump time. So in this case, we have actually not just one Poisson process, but we have d Poisson processes. Each Poisson process, has its own rate lambda I, depending on psi, okay, on the potential here, right? When the ith clock rings, we will flip the ith component of the velocity vector. And if you want to visualize it a bit more clearly, we will anyway consider a standard Gaussian for the as a limiting distribution for the position component. And so this is how your trace plots would look like. So we're moving linearly, and then there are these sudden changes of velocity. In this case, we're changing the v1, right? So the first component of the velocity, and so on. So again, for the rest of the talk, I will just consider standard Gaussian limiting distribution. Okay, so again, we need a time reversal formula for the zigzag process, right? This was our initial, it is our initial requirement to do generative modeling. The flow map, as I said before, will just be obtained by going backwards in time. So before we were going to x plus vt, right? Those were the linear dynamics, and in this case now we're going to x minus vt. And then the jump rates and kernels, we can enforce the balance condition that we saw in the previous slide. And it turns out that what we obtain are lambda I and qi as follows. So the qi is the easy bit. Qi doesn't change. Right? Qi is the same of the forward process. It will just correspond to flipping the ith component of the velocity. So this is nice. What is less nice, perhaps, are the rates. So the rates, again, depend on the forward rates, but with a flip in the ith component of the velocity. And in particular, have this factor, right? It's a factor of the probability mass, okay, of observing RIW velocity for the forward process, given that it is currently at y, at position y. So again, it's a conditional for the velocity given the position of the forward process. And let me remind you again, the forward process, of course, its law depends on the data distribution, because that is our initial condition. So this is something that we do not know, we do not have access to, and we will have to learn it from the data. Right, so again, as you can imagine, we will need some approximations. So the main one, and actually the only one, so, at least in principle, is the estimation of these ratios. Right, because we can just introduce this Ri function, which is the density ratio, and rewrite the backward kernels, okay, in this form. What we will aim to do is learn this Ri, so the density ratios, using a neural network, of course. So how do we do that? So we will just consider essentially a neural network, S theta, which takes as input the current position, the current velocity, and the current time, and outputs, okay, a d-dimensional vector, where the component 1 will be an estimate for R1, the first density ratio. So indeed, what we aim to do is to learn a theta star such that SI theta star is close to Ri. So these density ratios essentially play the role of the score, right? It's the same unknown object. Once we have such an approximation, what we can do is we just compare the true backward rate to this approximated version, right? So here we're just using our neural network instead of the real density ratio. So once we have this, then we have an approximation of the rates. So how do we do that? So the first thing that one can think of is, okay, we just emulate the score case, and we just take a square loss. So we just compare our approximation to the real density ratio. We take the square, and we're done. And as it turns out, if you just do maybe one line of computations, you just expand this square. Okay, what you obtain is that minimizing LE is equivalent to minimizing LI, okay, where LI is this object, so this integral, where, as you can see, there is no more density ratio. This is a completely computable quantity. Okay. And here the trick is that, well, the expectation is with respect to PT. So PT here will cancel with the PT that is at the denominator of the Ri. Okay. So you would think this is amazing. I mean, it was so easy to do. Great, we're done. Okay, but this loss is quite bad, actually. If you try to implement it, you will get a lot of nuns in your computer. Probably because you would need to enforce a lot of structure on the neural network, and it's not clear. That's not an easy thing to do. Okay, so this loss is really unstable. You can try to use it, but we didn't manage to make it work. Okay, so what can we do actually? So what we do here is we were inspired by this paper by Hivarinen from 2007, and this is quite interesting for me because Hivarinen is also the person who actually came up with the score matching framework, so the losses that we discussed before. And for him, the score matching loss was just a way to learn a probability distribution, to learn a model, okay, to model some data, so to learn a good representation of the data. And in the same way, he proposed a similar version of this framework to learn a good model for random variables on plus minus 1 to the d. So his goal was to learn a model q theta, okay, modeling v's in this space. Okay, and the way in which he was doing it was indeed considering density ratios. Okay. And doing this sort of ratio matching loss. And why is that? Well, because this ratio does not depend on the normalizing constant. So you don't need access to the normalizing constant of your model to learn this. Anyway, in our context, we don't want to do that. We want to learn just the ratio. But the way in which Hivarinen did that was by introducing this, this function g, which is a function that the goal is really to sort of regularize the problem a bit. So we want to avoid having infinite values of the ratios, or if we do, we want it not to give us nuns in the loss. Okay. And then this might seem a bit complicated, but essentially what we're doing is that, again, we're comparing our estimate for Ri with Ri and doing a square loss, but we just pass both values through this filter that is G. And why is that? Again, because G regularizes everything.
That's just that simple function.
Yeah, it's 1 over 1 plus R. And then also another thing that is different from before is that we don't only do it for xt and vt, but we also do it for xt and rivt. So we learn at the same time both the ratio that we observe and its reciprocal. And this again is, well, actually it's also the main reason, I guess, is because you want to be able to compute this loss, right? And if you didn't have the second term, you wouldn't be able to. It would depend on the true ratio, right? But if you do this choice, again, you can reformulate this expectation, just expand the squares and do a few computations, this time maybe 5-6 lines of computations. And what you get, again, is that the loss above is equivalent to this loss, where there is no R. There is no Ri, there is no P, PT, or whatever. So this is, everything is known here. It just depends on the neural network. And so this is a computable loss. And it inherits, okay, the properties of this guy, which is much better than before. Okay, so now, essentially we have a procedure to learn the neural network. Okay. And so we have learned the characteristics of the backward zigzag process. Okay. So here we have lambda I bar, which are our approximate rates. And again, the procedure so far would be, okay, we start from PTF, we go backward in time, we're done. Okay. But again, we don't have PTF. So what we will do is the same as in the diffusion model literature. We will just approximate PTF with a limiting distribution, which by construction for us in these slides, it's just a Gaussian. Okay, so already we have two approximations in this model. Well, what we can do is we can actually obtain a bounding total variation distance that we will get to in a second. What we will need to assume, okay, I will just show it to you. The bound is the one at the bottom of the slide, and it's a total variation bound between the data distribution mu star, which is unknown. Okay. So for me, it's a bit magical maybe, and the law of this backward process that I showed you before. So the process that starts from the limiting distribution and uses the approximate rate. Okay. And we see it's a sum of two terms. We have a first term which is due to the limiting distribution error. So here, because we are approximating PTF with the Gaussian. The second term is due to the error in the backward rates, in the approximate backward rates that we're using. Okay, what we assume to get this term is indeed the assumption above. So what we are saying here is that in expectation, we want a bounded error. Okay. So here, Ri lambda I is the real backward rate. Si theta lambda I is the approximate backward rate, okay, obtained with the neural network. So we want that in expectation we have bounded error. So, okay, this is a strong assumption, but it's not different from any of the diffusion models literature. Okay, so you have to assume that you're not doing something really stupid.
And you think that it's actually going to be like this? Having this linear increase with TF? So is that just a bound, or is that no the other two?
Sorry, this.
Or is that going to be a real fact of life?
Well, this I think this is it's not so bad.
Not so bad.
I think because this assumption is quite. It really means you're doing things right, and okay, there's no real way of knowing that. Actually, there are very few papers that prove bounds. I mean, I think this is an interesting field.
The error you make will be linear in...
No, sorry, in that case, in that sense, no. Well, okay, you will do multiple steps. There are a few things coming into play. So, of course, you could say I'm accumulating error by using the wrong rates. So if I use the wrong rates for a time TF, the more I go, the more I will make a mistake.
It should be linear. So that
because you don't learn anything for some time, you have completely forgotten new stars. The neural network is supposed to do nothing.
Yeah. So I mean, it's just I'm not sure if it's what happens in fact.
That was my question.
I hope not, but it makes sense that we are a bit accumulating error by using the wrong rates. But maybe M depends on T, right? Because for a large T, it's easy, because the density ratio converges to 1.
Yes.
Trust me on this if you
No,
don't.
I understand that, of course.
So in that case, you could say MT decreases with T. And so you have a balancing out of the effect.
Then it's not as bad a term.
Yeah, hopefully not. Yeah. All right. Okay, going back to what I showed you before. So we now have two sources, two approximations that we already had to do. And the third one is, okay, how do we simulate the zigzag process, right? So it's something, it's not a new topic for me, perhaps, right? And also for some people in the audience. But the main issue, and of course we also heard a bit from Paul Fernhat yesterday about it. So the main issue with the simulation of a PDMP is the need to simulate, okay, the event times. So now we have our backward rates, our approximate backward rates, lambda bar, and we will need to obtain the next event time by solving this problem. So this is just a way to simulate a non-homogeneous exponential distribution. Okay, so I'm not writing anything strange. If you don't know, trust me, this gives you a sample from this distribution. And again, here we will have to integrate, right, lambda bar I along the dynamics. So here you see time is going forward for the backward process. So okay, it's actually going backwards. And here we're following our flow. Now, if you plug in the rate that we have found, what we get is here we are integrating a neural network. It's not so nice. I don't know how to do that, at least. Okay, so here we will need, similarly to diffusion models, we will need a further approximation. We will need to find a way to approximate this mechanism. Okay, and so actually this is something that we worked on with Joris or Pierre Montmarché, indeed, Paul Dobson. We know how to build a Markov chain that approximates the backward process. And so this is essentially, if you think of the SDE case, we could just say, okay, we just do an Euler scheme of the backward SDE, and we're done. Well, pretty much the same thing for PDMPs. So the idea in the case of PDMPs, instead of freezing the gradient, is to say, well, that integral you saw before, I will just approximate it by, again, freezing the integrand at time 0. So, okay, with, s equals 0. And then I multiply by the length of the interval. Just, this is the easiest thing you can think of. And both approaches that we worked on essentially rely on this idea, right? Maybe not directly, but what you do in the end is indeed you freeze your rate. Because then things become easy. Okay. Of course, you will have to be smaller, and so you will choose a small step size, and you will do this every time. Okay, and so from now on, I will just use an approach based on splitting schemes that I don't want to discuss because otherwise it will take too much time. But the idea to approximate the backward PDMP is then the following. So we will just introduce a sequence of step sizes such that their sum is equal to the time horizon. Okay, and then we just do this simple algorithm. So we start from the limiting distribution of the forward process, and then we do n steps, where each step is obtained by applying the transition kernel corresponding to the splitting scheme approximation of our process. And then we output x bar n, which hopefully will be approximately distributed according to mu star. So hopefully in the sense that we need to do the learning well. And actually also choosing a good sequence of step sizes. Okay, there are many things to do well. And what we obtain is now our final algorithm. So now we have put all the pieces together. We have seen how to approximate the characteristics of the backward process. We have seen how to approximate the limiting distribution, how to approximate PTF with the limiting distribution, and we know how to simulate the backward process. Okay, so now we can go to some numerical simulations just to validate a bit what we saw. No, dogs is not so, it's a high dimensional, I would say. So it's a work in progress. Okay. So we started with some 2D data, okay, but difficult 2D data at least. So above you see the real ones, so the data sets we train our model on. And in the second line you see our generation using the zigzag process. Okay. So again, these data sets are not easy. Okay. So especially the rows and this fractal tree are quite tricky, I would say.
The drawing picture is fixed, but you have different realization of nodes.
Exactly. Yeah, so what you will do in the end, if you think of the expectation that I showed you before, this is a good question. I didn't talk about it. Essentially, you will do this multiple times. Okay, so you do several iterations of the following. I subsample the data points. For each data point, I sample a time. I go for each data point, I simulate forward in time with the corresponding time. And with these samples, I approximate this expectation. Okay, then I do one step of gradient descent or more. Then I repeat. I subsample again the data points. I use them to approximate E, and I go on like that.
Can I just clarify that? So
yeah.
In those examples, the target density is what? It's like the distribution of those points. Is that right? It's like uniform on the picture? Or
so the fact is that you don't really care about what's the target density. You just need the data, right? So this is the way in which they are generated is just, I guess, like you take uniform realizations over each rectangle.
But you have 50 of these on the left in your data set. There are 50 checkerboards, or it's just one?
No, there's just one.
What is confusing, I guess, is that in images usually each picture is one data point here. In fact,
is one
not
point.
A picture, it's a lot of points.
Yeah, sorry, okay.
This was what we were confused. I
Okay.
was confused with.
Yeah, no, that's a good point. Yeah.
But don't you also need to simulate the forward dynamics when you're doing your training?
Yes. So you start with 1 point.
Right.
You randomly choose 1 point in your data set.
Yeah.
And you simulate it forward in time for a random amount.
So what are the forward dynamics?
Zigzag.
With what rates?
With the Gaussian. No, yeah, we just working with the
It's
Gaussian.
just going to Gaussian, I see, right.
Yeah.
Yeah.
So the limiting, you go to the limiting distribution, which is just the Gaussian
Yeah.
on the speed, on the position, and on the velocity, just the uniform.
Got it.
Yeah. No, but it's good to ask these questions because actually, I mean, there's a lot of things that are a bit hidden in these models. Anyway, so this is the result for the 2D data.
So these are, excuse me, but
Yes,
these
no,
are
no.
5 different simulators, 5 different things that you should.
Yeah. So you should just compare these two. Okay, these
That's
two.
what was,
Yeah. Okay, and you might wonder, what's the performance of this? So here we compared to, constraining to the Rose data set, we compare to IDDPM, which is one of the denoising diffusion probabilistic models, but the I stands for improved. So it's a good model. Okay. And we compare it to our EMPs in terms of computation time. And what we see is that in the end, we always outperform IDDPM. Here, I don't have just zigzag. Okay, I will also have randomized HMC and bouncy particle sampler. Zigzag is the one that gives us the best performance, and it's actually it's the maximum mean discrepancy. So, yeah, good question. Thank you for pointing that out. Okay. So it's just one of the classic ways, classic as in it's a 2-year-old field, but classic ways to compare realizations. Okay, and if we want to do something a bit more high dimensional, we can also consider a data set that is composed of MNIST digits. Okay, so these are just handwritten digits, so this is a bit more high dimensional. And this is again obtained using zigzag. We can obtain these generations. Okay, so these are not too bad. Okay, so we can move on to the conclusions. So essentially what I discussed was a generative model on essentially really just for zigzag. No one asked about it yet, but actually the loss function that I showed you had a bit of a computational problem in the sense that you needed to pass through the neural network t+1 times per data point. So this is way too much. So in the paper, there is also a way to go around this. Essentially, we're making a sort of an assumption on the process, but which is verified in practice, as it turns out. And we get a loss function that is just order 1 in the dimension per data point. And so this is what we use to obtain the MNIST digits. I didn't explain it because it's not that easy to explain the way in which we implement it, but in the paper we also consider other PDMPs, so the bouncy particle sampler and randomized HMC, and we build generative models also based on those. The difference with the, let's say, RHMC is that, okay, we will have Hamiltonian flow, which is easy. You just revert time. I mean, if you target a Gaussian, it's easy. Okay, but you will have velocity refreshments. So velocity refreshments, if you take the backward kernel of velocity refreshments, it means you will have to sample from the conditional density of V given X. So you don't only need to approximate ratios, but you will need also to sample from these densities. And we did that using conditional normalizing flows. very painful objects to work with, though. So you can make them work, but it's not as easy as it is for zigzag. Okay. So this is also something we're still working on and trying to improve. And in general, indeed, we're still improving everything, and because there's a lot of engineering behind these models, so slowly we are getting better and better performance. Okay. And hopefully we will continue to do so. Okay, so I leave you with the reference for this for the talk and for all the things that I cited in the presentations. Thank you for the attention.
Any questions from Andrea? Yeah.
Yeah, thanks for a nice talk. So maybe on slide 20, I think it's about slide 20, where you have this loss function.
Yeah.
I think you made this change to it, this function. I was just wondering, to some extent, this backward process, you do some conditioning, so how do you even know that this expectation is finite, this loss function? Is that obvious?
Yeah, so that's exactly why you introduce G. Because if we go to the previous formulation, so the basic one, here what happens is indeed you have that this is in practice, okay, when I implement it, this is infinite, and I'm done. I cannot go forward, I cannot learn anything.
Perhaps there are some sort of restrictions what you could take on this SI, right?
Yeah, but
Which would ensure it is the right behavior. That's one part, and the other part of this function will just be the flexibility of the neural net, but then you should ensure properly that this function is bounded.
Yes, but we tried to enforce these things, but I think it seems that the most you enforce on a neural network, the worse your life becomes. Okay, so I mean, you just shouldn't think, you shouldn't mess with them too much. In my limited experience, at least. So anything we did to enforce some structure failed in this loss function. And the reason really why we considered in the end this loss function is that this is bounded. 1 over 1 plus r is bounded, below and above. So here you cannot have any numerical instabilities. Even if your SI is infinite, well, this doesn't matter.
Sure, but it feels a bit arbitrary.
Well, you can do, actually I think this is a problem that is not that different from choosing an acceptance-rejection ratio in Metropolis Hastings or in Barker, right? I think you can even use 1 minimum R instead, and this still is, you can work with it, right? So it is arbitrary as a function. You just need something that is stable and allows you to reformulate this loss in a way that does not depend on Ri.
Yeah, okay, I see. For Metropolis Hastings, I mean, it's far from arbitrary. You need to preserve something, that there are a few choices.
Yeah, it's far from arbitrary today, but no, but it's a good point. I mean, you can do many choices here, but this works decently. Yeah, that's a good question. Yeah, any maybe starting from you.
In the fictions, just understand it's
Yeah, sorry.
So in here, 1 day of points, there's R2.
1 point is on R2.
But in these applications, you really want to come back and generate a picture that's in many dimensions, right?
Right. Yeah. No, for sure. I mean, of course, you want to generate a movie if you can, but you have to start somewhere. So this is a simple yet not as simple as it could be example. And the MNIST.
Write a math paper.
Sorry.
Write a math paper. By this process.
Yeah, exactly. Yeah. Yes.
I actually had a related question. So, when comparing these different data sets, can you give us some intuition which ones were hard for this method and which ones were more easy? Was there something surprising?
In these simulations?
Yes, in these,
in
or
general.
maybe other examples that you consider.
Yes, so, okay, nothing specifically I would say about, I think these are, again, these two cases are a bit more difficult, perhaps, just because, I mean, you need a lot of detail but it's still doable. And the difficulty again here is that it's relatively speaking high dimensional. And so here is where actually we realized we had to do something else with the neural network to make it lighter, to make the loss function order 1 in the data, in the dimension of the data. And then we could obtain these. So when you go higher dimension, everything becomes more challenging. And if you see how these methods are built, there is a lot of tuning parameters, a lot of engineering to make them work on images. So you see a nice picture and you think, it's easy, it works, but it's not so easy if you're not a computer scientist, essentially. So yeah, when you go higher dimensional, that's the real issue, actually.
Christoph?
So I've expected the generative models to generate new images.
Yeah.
And basically the images that you produce are just noisy versions of what you got in your initial distribution.
In this case?
Yeah, you have expected, the generative models to combine images and...
Right, but in this case, I mean, there is no image, there's just data points. So what you expect in that is you learn where the data points come from, right? It's hard to compare each point to each point, right? So what I'm saying is, I mean, I understand your question. This is more...
It's the beginning.
Yeah.
It's the beginning.
But this is more clear from these digits, right? So these are not in the data set, for instance, I guess.
That's my question, that basically you seem to say that basically you produce things that look very much like the training set.
Yeah.
But is that the aim of a generative model?
Well, yeah, I mean, you can, there are methods to compare what you obtain to what is in the data set, and you can see what's the closest data point to your generation, right? And of course, you don't want that to be 0. You don't want that distance to be 0.
The question is, again, the discussion we had of what is the distribution, and in fact, in the previous pictures, it's not data set of pictures, it's data set of 2D points, which are distributed according to this. So you are not recovering a new picture, you are recovering new dots in 2D. So you are indeed doing generative. It seems to me this is the...
Yeah, so that's what I was trying to say. I mean, you cannot really, it's hard here in this case to compare where, it's not really images, right? Here we're showing many images in the same plot. And so what you hope is, I mean, in the end you should recover the probability distribution that generated the images. And in this case, you should recover the probability distribution that generated the rows or the fractal tree. So this is not really wrong. You don't want to have realizations that are completely out of sample, because that's not your task.
It's an image also. It's a rows image.
It is, but it's many data points.
It's easy to get misled by it.
Yeah, okay, now I understand.
Maybe one final question, if there is someone. Yes?
Considering simulating the approximate time reversal process, I believe that given that neural network is automatically differentiable, we can do Poisson thinning and do that exactly, without incorporating any numerical errors.
How would you do that?
I would say by automatic differentiation, you get first you have a grid, and then compute the tangent of the neural network score function, and then upper bound with that, and do Poisson thinning.
Okay, this is still approximate, all right? It is still approximate, I would say.
If your activation function is bounded, and you have a deterministic bound on your activation function, you can...
But we don't have that, right?
You could, I mean, you choose your
But the ratios are not bounded. So, I mean, you're modeling something that is not bounded, so...
We do have to fix a small amount, so that, and do only in a really, really short time interval.
Right, but this is, again, it's an approximation, I would say. Right. So it might be that the error that you obtain is smaller if you compared to an Euler scheme or so, but it's nevertheless an approximation, I would say.
That might also possibly.
Yeah. So yeah, there are many choices there that you can. Sure.
Right. Okay. Let's thank the speaker again.